Lab number 5 is our second in a series of OSPF videos. Specifically, lab number 5 focuses on multiple areas and frame relay non-broadcast. To begin with, we're going to see the characteristics of a non-broadcast OSPF network type. We're going to discuss the characteristics of multi-area OSPF networks. Then, we're going to take a look at the concept of a virtual link. We might need a virtual link if we have one network area that is not directly adjacent to the backbone area, to area 0. Then, we'll take a look at the syntax for OSPF configuration, and we'll set up OSPF for multiple areas. Next, we'll configure OSPF for the non-broadcast OSPF network type, and we'll set up one of those virtual links. Finally, we will verify our configuration.
In this lab, we want to illustrate a characteristic of the non-broadcast OSPF network type. The non-broadcast OSPF network type is the default, by the way, on frame relay serial interfaces. And with this network type, unlike in the previous lab, where OSPF neighbors dynamically learn about one another, with a non-broadcast OSPF network type, the OSPF peers do not dynamically learn about one another. In fact, we're going to have to go in and use a separate statement. We'll have to use a neighbor statement to educate these routers about one another. And something else to be aware of in this non-broadcast OSPF network type, all of the routers are part of the same subnet. That's different than in previous labs. I'll show you the topology in a few moments, and we'll see how these routers actually are on the same subnet. And unlike the point-to-point OSPF network type that we saw back in lab number 4, here with a non-broadcast OSPF network, there is a designated router that is elected. And we're also going to have multiple OSPF areas in this lab. If you remember, in lab number 4, we discussed a big benefit for having multiple areas. We could constrain the flooding of link state advertisements, LSAs, to within an area. So if there's a network change, that change does not have to be propagated everywhere throughout the entire OSPF topology. That flooding could be constrained in an area, and then, as we'll talk about in the next lab, we could send summary information, if need be, from one area to another area. So this is going to reduce the flooding of route changes throughout the topology. And when we do have multiple areas, one area serves as the backbone area, and that backbone area must be numbered as area 0. Another restriction that we're going to illustrate in this lab is that every other area, it must be physically adjacent to area 0. In other words, if I had a router and one of its interfaces belonged to area 0 and another interface belonged to area 1, that would be fine because area 0 was present on that router. Or if another router had all of its interfaces in area 1, that would be fine because there would be an area border router, an ABR, that connected area 1 back to area 0. However, what we're going to see in this lab is that we have a discontiguous area. We have an area that has no direct linkage back to area 0, and that is going to cause us an issue. We will illustrate, however, how to overcome that issue using a virtual link. A virtual link can be used when we have an area that is not physically adjacent to area 0. What we can do is go into an area border router for area 0 and an area border router for that discontiguous area, and we can form a virtual link between those two routers. We'll take a look at how to do that in this lab. But for now, let's check out the topology we're going to be working with. A few things have changed in our topology since last time. For example, in lab number 4, all interfaces for all routers belonged to area 0. We only had a single area. Now you'll notice we have 3 different areas. Area 0, Area 1, and Area 2. And it looks like we're violating an OSPF design rule, doesn't it? Area 2 does not appear to be adjacent to Area 0. That can cause us an issue. We'll overcome this discontinuity using a virtual link in this lab. That's going to make router R2 appear to be adjacent to Area 0. Something else that has changed since the previous lab is that now routers R1, BB1, and BB2, they're now part of a non-broadcast frame relay network. Specifically, instead of using sub-interfaces as we did previously, now router R1 is connected into the frame relay cloud via its serial 0/0 interface, the physical interface rather than the sub-interfaces. And the same goes for routers BB1 and BB2. We have a couple of PVCs, permanent virtual circuits, built on these physical interfaces. Those are still in place, but you'll notice with this non-broadcast configuration, all of the routers connect into this frame relay cloud as members of the same subnet. Everybody is a member of the 172.16.1.0/24 IP address space. Previously, we had one network between R1 and BB1, and another network between R1 and BB2, and a third network between BB1 and BB2. Now all of these routers have their serial 0/0 interfaces as a member of the same subnet. And something we're going to notice about this non-broadcast OSPF network type, the neighbors are not going to be dynamically learned. So we will need, for example, to go into router R1 and educate router R1 about routers BB1 and BB2. And we only have to educate one end of a PVC, by the way. We don't have to have a configuration on both routers at each end of the PVC. But after we educate router R1 about its neighbors, we still have a PVC over between BB1 and BB2. So we'll go over to one of those routers and we will enter another neighbor statement to make sure that BB1 and BB2 know about one another. In fact, let's take a look right now at the syntax that we're going to be using. Some of the syntax that we'll use in this lab is the same syntax that we used back in lab number 4. For example, we will still go into the router configuration mode by saying router OSPF and giving a locally significant process ID. We will still educate the OSPF routing process about the networks we want to advertise in a particular area with the network command as we see on screen. A command that we did not see last time in router configuration mode is the neighbor command. We say neighbor and we follow the neighbor statement with an IP address, the IP address on the other side of a permanent virtual circuit. For example, from the perspective of R1 based on the topology we just saw, we would say neighbor 172.16.1.2 to point router R1 to the backbone router of BB1. That's BB1's serial 0/0 interface. Once we did that, then BB1 and R1, they could establish an OSPF adjacency between themselves. We're also going to have an issue with an area that is not attached to area 0, and that's going to be area 2. We're going to fix this discontinuity with a virtual link. The way we're going to create a virtual link is by going into routers R1 and R2 and entering the command you see on screen, area followed by a number. That number, by the way, that's the number of the area that we have to transit to get between the backbone area and this discontiguous area. In our example, that transit area is going to be area 1, so we will say area 1 virtual-link followed by the router ID of the router at the far side of this virtual link. So on router R2 we will give the router ID of R1, and on router R1 we will give the router ID of R2. That's the theory and the syntax. Let's now go out and walk through the configuration together. Let's begin our configuration on router R2. First, let's go into global configuration mode and we'll enable the OSPF routing process by saying router OSPF, and we'll give a process ID of 1 as we did in the previous lab, and we have 3 different interfaces that we want to be advertised via OSPF. Notice that our Fast Ethernet 0/0 interface as part of network 10.1.2.0 is part of area 2. Our loopback interface is part of area 2, but we have another interface, Fast Ethernet 0/0, that's part of area 1. We belong to 2 different areas. So we're not going to be able to use our shortcut that we talked about in the previous lab where we give a single network command to say everybody belongs to the same area. We're going to do these individually. Let's say network, and we'll say 10.1.2.0, and I'll give a corresponding wildcard mask. For our 24-bit subnet mask, we say 0.0.0.255, and this is a part of area 2. What about the loopback interface? We'll say network 2.2.2.2 with a corresponding wildcard mask of 0.0.0.0. That is a member of area 2. Next up, we say network 192.168.1.0. This is a 30-bit subnet mask, so the corresponding wildcard mask would be 0.0.0.3, and you'll notice that this network on Fast Ethernet 0/0, it is a member of Area 1. So we say Area 1, and we've done our initial configuration now on router R2. Let's go over to router R1, give a similar configuration. On router R1, we say router OSPF 1, and we want to advertise network 192.168.1.0 with a 30-bit subnet mask as a member of Area 1, just as we did over on router R2. What about the loopback interface? The loopback interface, we're going to make part of Area 0, the backbone area. We'll say network 1.1.1.1, 0.0.0.0, area 0. Next we say network 172.16.1.0, and this has a 24-bit subnet mask. We say 0.0.0.255. It's part of Area 0. You'll notice this is a big change from our previous topology. Now, instead of using sub-interfaces to leave router R1 going out to the backbone, now we're just using interface serial 0/0, and we have a couple of PVCs built on that physical interface. So all of these routers, they belong to the same subnet. A little bit different than what we did before. And you'll notice that we just had an adjacency form. We have a neighbor, an OSPF neighbor in router 2. Notice the 2.2.2.2 router ID. I think we're done now on router R1. Let's go over and configure OSPF on router BB1. As we did before, we'll go into router configuration mode for OSPF process ID 1, and we'll say network 172.16.1.0 with a 24-bit subnet mask. That gives us a wildcard mask of 0.0.0.255. This is a member of Area 0. Let's give another network command. This is for the loopback interface. We'll say 3.3.3.3 with a wildcard mask of 0.0.0.0. And this is a member of Area 0 as well. Only one router to go. Let's go over to router BB2. And on router BB2, we'll go into global configuration mode once again. Router OSPF 1. And we'll say network 172.16.1.0. 0.0.0.255 as the wildcard mask. This is participating in Area 0. And now for the loopback interface, and that's going to be network 4.4.4.4, 0.0.0.0, Area 0. I think we're now done with all of our network commands for our OSPF configuration. So let's go back over to router R1 right now. That's sort of the central point. And let's see how things appear from the perspective of router R1. To begin with, let's do a show IP OSPF neighbor command. And at this point, we only know about one neighbor. Interesting, look at this. We only know about router R2 as our neighbor. Why do we not know about router BB1 and BB2? You might recall from our discussion previously that the default OSPF network type for a frame relay serial interface, as we have here, the default OSPF network type is non-broadcast. In fact, let's just verify that interface serial 0/0 on router R1 is acting as a non-broadcast OSPF network type. We can do a show IP OSPF interface command followed by serial 0/0, and yes indeed, we have a network type of non-broadcast. This means that router R1, it's not automatically going to learn about its OSPF neighbors. It's not going to dynamically know that BB1 is a neighbor and BB2 is a neighbor. We have to explicitly configure that. Let's see how to do that. First, we'll go into router configuration mode for OSPF process ID 1, and we'll give a neighbor statement. We'll say neighbor 172.16.1.2, which is, as you can see from the topology, that's going to be the IP address of the serial interface on router BB1. That's going to be one of our neighbors. We'll give another neighbor statement. We'll say neighbor 172.16.1.3. That's going to be router BB2, 172.16.1.3. You'll notice after issuing those commands that we had a couple of status messages pop up. It looks like we have now formed neighborships with routers BB1 and BB2. That's good news. Let's verify that. Let's do a show IP OSPF neighbor command, and it looks as if we now know about a neighbor of R2, a neighbor of BB1, and a neighbor of BB2. Things are looking much, much better now. And you'll notice for R1 to form these adjacencies with BB1 and BB2, we only had to configure the neighbor statement on one end of the PVC. However, if you'll notice, we have another PVC between routers BB1 and BB2. We need to educate those routers about one another as well. Let's do that from the perspective of router BB2. If we go over to router BB2 and get into router configuration mode for OSPF process ID 1, we can say neighbor 172.16.1.2, the IP address of BB1's serial interface. At this point, all of the routers should know about one another. We can see on screen that an adjacency just formed between BB1 and BB2. Let's verify that with a show IP OSPF neighbor command. We probably should be in privilege mode when we do that. Let's do a show IP OSPF neighbor command. There we are. And we see from the perspective of router BB2 that we know about BB1 as a neighbor, and we know about R1 as a neighbor. Let's now go over to router BB1, make sure things look good from its perspective as well. Let's do a show IP OSPF neighbor command. Looks good. We know about router R1. We know about router BB2. Finally, let's go over to router R1 and let's do a show IP route to make sure that we have reachability to, for example, the loopback interfaces connected to BB1 and BB2. We do seem to know about the 3-dot network and the 4-dot network. That's good news. However, something's still not right. If you'll notice, router R1, even though it does have knowledge of the loopback interfaces on BB1 and BB2, it still does not have any knowledge of this 10.1.2.0 network or the loopback interface of router R2. These networks, remember, live over in Area 2. Why is that? You might remember one of the requirements for a multi-area OSPF network. That requirement was that every area had to touch the backbone area. It had to be adjacent to Area 0. And if you'll notice in our topology, Area 2 is not adjacent to Area 0. Rather, Area 2 has to pass through Area 1 in order to get to Area 0. What can we do about that besides redesigning the network? One option is to create a virtual link. A virtual link will virtually tie together Area 2 with the backbone area. We can say that we will pass through Area 1 to get between these two areas. Here's how we can configure that. We need to do the configuration from the perspective of router R1, then we'll go over and configure the other end of the virtual link. on R2. Since we're already on R1, let's go into router configuration mode for OSPF process ID 1, and we'll say area. We'll give the area number that we need to transit to get to the other side of this virtual link. In our example, we need to transit area 1. So we say area 1 virtual link, and then we give the router ID of the router at the other side of this virtual link. From the perspective of R1, the router at the other side of this link is going to be router R2. It has a router ID of 2.2.2.2. We're done with our configuration on router R1. Let's move over to router R2 and let's give a complementary configuration. We go into global configuration mode and we say router OSPF 1, and then we say area 1, because that's the area that we're going to transit virtual link, and we give the router ID of, in this case, router R1. We say 1.1.1.1. Notice that we have a message that just popped up telling us that we now have an adjacency with router R1. But didn't we already have an adjacency? We did, but we were not exchanging routing information over that adjacency, were we? No, in fact, let's do this. Let's go back over to router R1 right now. And from router R1's perspective, let's do a show IP OSPF neighbor command. Notice that we have a couple of adjacencies with router R2. One over the physical fast Ethernet link, and one over this virtual link that we just created. This is going to allow router R1 and router R2 to exchange routing information with one another. Let's prove that. Let's do a show IP route, and look at this. We now have knowledge of that 10.1.2.0 network residing over in area 2. We also have knowledge of router R2's loopback interface, which is 2.2.2.2. And something else that's interesting to note, notice that those routes that are coming from a different area other than the areas that router R1 resides in, notice that they are tagged with an IA. If we look at our context-sensitive help, we can see that IA refers to an OSPF inter-area route. This route information is coming from another area, in other words. Finally, just to make sure that we have full reachability to all of the routers in the network, let's do a ping to all of the routers' IP addresses, all of their router IDs, in other words. Let's do a ping to our own router, ping 1.1.1.1. That was successful. Let's do a ping over to router R2 at 2.2.2.2. We'll ping router BB1 with an IP address of 3.3.3.3. And finally, let's ping router BB2 at an IP address of 4.4.4.4. That is how we configure a multi-area OSPF network when we have a non-broadcast OSPF network type, and even when we have an area that's not physically adjacent to our backbone area. That is going to wrap it up for lab number 5, where we configured a multi-area OSPF network where one of the network types for OSPF was non-broadcast. We noticed that non-broadcast had the unique feature of not allowing the neighbors to automatically learn about one another. We had to overcome that behavior with the neighbor command. Something else we observed was that if an area was not physically attached to Area 0 in a multi-area OSPF network, then it would not be able to exchange routing information with any other area. A fix for that we demonstrated was the creation of a virtual link that would tie together this other OSPF area that was discontiguous from Area 0, the backbone area. And one of the things we noticed toward the end of the lab was that from router R1's perspective, a couple of the routes showed up as inter-area routes they were being advertised from an area that R1 was not directly attached to. We're actually going to take that concept and build on it in our next lab, where we start to see how we can summarize routes coming from another area. And what if routes are coming from an external routing protocol, something other than OSPF? There's a different way that we can summarize routes into OSPF. We'll take a look at both of those scenarios coming up next in lab number 6.